remember what we've done so far. So we first started off with an individual z-test, which we'll never do again. Nobody does studies on individuals, right? But I had to teach it to you to kind of set up the process. Then we learn a sample z, which we'll probably never do again because that requires that you know population stuff, parameters, and we just aren't going to go around knowing things. The only people I see doing sample z's are sociologists. They tend to look at like death records and things that you can actually access the entire population. So they might do them, but you'll probably never do a sample z. Then we moved on to a sample t. That's something that you're going to see published in literature. It's something more likely that you'll actually see do yourself, because I assume you're all going to go on to grad school and do statistical things. So we looked at one sample z, and then we moved on to a dependent t. And sometimes people call a dependent t a two-sample, right? Because we've sampled somebody twice, so we've sampled mothers and fathers, so there's two sets of samples. But essentially, it's really a one sample t. Everybody got the different, we were just looking at the different scores. So it was like a sample t, something we're going to see more of. And so I'm just trying to go slow, make sure we're all on the same page so far. Everybody feeling good about this process? All right, now today we're going to do an independent sample t. And this is really where we have two independent samples. That's why we call it an independent t. I think it really can help to understand why we call them the way we call them so that you know what test is necessary. So a dependent t was like two samples, but really it was just that one depended on the other. So it was a before and after. The difference depended on where you started and where you ended. So dependent, dependent. If we were looking at if mothers and fathers agree on how smart their children are, well, the mother's score and depended on the father's score, or the father's score depended on the mother's score, depending on which child they were talking about. Independent t now is where we're going to look at two randomly separate groups. So it might be something like Saddleback College students versus New York City college students. They're not both taking classes. I couldn't say IBC because some of you take classes at IBC and some of you take classes at Saddleback, right? But maybe I'm just looking at totally different students. Saddleback College students versus New York City college students. And so they're two independent groups, not related in any fashion, and we want to see how their data are different. So it might be a placebo group and a treatment group or things like that. So this is what we're going to do today. So you feeling okay with our list and how they're related? So what I want to point out is where we're going next time is the next thing here is an ANOVA, and this is where we have three or more groups. So just so you can sense the pattern, we went from a person to a group, to a group, to a little bit more complicated group setting, right? So it's like twice. Now we have two separate groups. Now we're going to have three or more separate groups, just so you can pick up the pattern. This is what's going to be on the next test. So it's going to be important that throughout this week and next week, that we really kind of start to differentiate between these so that you understand which one's necessary. On Wednesday, I have an activity where we really explore what goes into these two tests so that just by looking at the prompt, you can tell which one's happening. So you know what thing to click on if you're doing JASP or how to interpret the results. I found that ever since I started that activity, it's kind of like group work. We break up into groups. Students really start to understand how to tell when it's a dependent T versus an independent versus a one sample. So I'm just putting that on your radar because if you hear words that trigger you to go, oh, now I know the difference, then write them down so you don't forget. Because this is what's going to be on the next test. But this is what's going to be in life, right? We have these statistical approaches, and when you all move on to greater, bigger things, I would like you to know which test was necessary. So even though JASP is going to do a lot of the legwork for us, I'd like you to know which thing you're supposed to click on. So if you haven't already picked up on the pattern of how I teach this, I usually start with a theory as to, can you get it? Yeah. You can grab that for him. I just don't want somebody else falling. There's been too many today. I usually start with the theory as to why the first test didn't work, how the new one works, and then we move into the 6 steps to inferential statistics on the new test, right? So today is just going to be the theoretical day of why we can no longer do the one sample t or the dependent sample t formula when we have an independent sample t. So we're going to discuss theory today. And it can be quite an intimidating formula. So I would like to just go super slow and make sure you feel confident on each of the levels. Yeah, don't look at it, it'll scare you. So make sure that you stop me when I've said something. It's really slippery right there. Okay. Make sure you stop me when I've said something that doesn't quite click. I want it to click before I move on. Don't look. No, don't look. It'll scare you. Put it away. Put it away. I'm just teasing. You can do what you want, but it will intimidate you. So my job is to make it not intimidating. I'm not going to ask you to do these formulas by hand. That's what JASP is for. But I want you to understand why they work. That's my goal in life, is to make you understand why statistics works. So remember when we had the situation where we had, okay, here's our distribution, and I'll put it here. We have this formula that said t equals x bar minus mu divided by s this time, standard deviation, divided by the square root of n. Everybody remember that formula? And remember that this denominator is known as the standard error of the mean. Does anybody remember why we have to have the standard error of the mean in the denominator? We didn't need that when we were doing this one, but we needed it when we were doing a one sample t. Or sorry, we didn't need it when we were doing the individual, but we needed it when we moved into the sampling. I'm glad you asked. So remember what we were doing before is we had this distribution, and we wanted to, instead of looking at just a score, we wanted to look at a mean. And so what we had to do is do a baby sample, baby sample, baby sample, baby sample, baby sample, and then we flooded those baby samples into a distribution of means. So these are x bars, these are x's. Is that sounding familiar? The mean was the same, but the standard deviation for the distribution of means was simply the standard deviation of the raw scores divided by the square root of n. So we have this in the denominator of our one sample t. We added in a one sample z, so we're using sigma. Then we also did it in a one sample t, we just changed it to s because we're looking at samples. Once we moved from an individual to a sample, we had to start using standard error of the mean, otherwise known as sigma divided by the square root of n, or s divided by the square root of n. So all of these, because we started sampling, are going to require this in the denominator. Instead of just sigma, we had to put a sigma divided by the square root of n because we're now looking at samples. That makes sense? So anytime you do sampling, we have to add the square root of n in the denominator. All right. So that was where we were last week. Now I'm going to add another sample. So now I have group A and group B. Group A has its own mean. It has its own, we'll say sample mean, its own standard deviation, its own sample size. And now we have group B. Let's say this is the New York City college students. They have their own mean, and then that means they're going to have their own sample mean. I don't mean to be going between lowercase and uppercase. That was not I'll just keep it lowercase. And they have their own standard deviation and their own sample size. So now, instead of dealing with just one distribution minus the mean divided by the standard deviation of the sampling distribution of that mean, I now have two. So together, we're going to build the formula that is the t for the independent, sorry, the t calculation for the independent t. Go, start over here. All right. So first, let's see if we can map onto what we know. It was x bar minus mu. How many x bars do I have now?
2x.
2. So I'm going to do, and it doesn't matter whether I go xa minus b or b minus a, but I'm going to do x bar a minus x bar b. Now how many mu's do I have? 2. Minus mu a minus mu b. Everybody with me so far? Then I'm going to divide by, now remember, this is called the standard error of the mean. It was also denoted S sub x bar, right? That was the symbol for it. So now I'm interested in the distribution of mean differences. What that means, or what that implies, is if I wanted to know if this mean is different from this mean, I'm going to take a baby sample, baby sample, baby sample, baby sample, and subtract this baby sample, this baby sample, this baby sample, this baby sample, take the differences and create a distribution of mean differences. That one was a distribution of means. This one is a distribution of mean differences.
I have a question.
Yes.
Does it matter the order that we do it in? Like if we do x bar b minus x bar a?
It doesn't matter, it's all legal. What I'm going to tell you is when we're doing it in JAF, you should always put the one that interests you first. The one that interests you first. So let's say I was doing Satellite College versus New York City College. Who are we truly interested in? Satellite College, so we'll put Satellite College first minus the New York City. So it's just good habit to put the one that you'd like to interpret first, but mathematically it doesn't matter. We're allowed to do whichever one. Did that answer that? So like let's say I was doing placebo versus treatment group. Which is the one I'm really interested in?
Placebo.
Treatment, because I want to see if the treatment worked. So I put treatment minus placebo, and that way if it's a positive number, it shows the treatment made you go up.
Oh, okay.
Yeah. So mathematically, you can do whatever you want to do. In terms of good form, it's good form to put the one first that interests you the most. So that was a great question. So if we could have done b minus a or a minus b, but you'll just want to see whatever storyline we're doing, the one that interests you is going to go first in our math. Good. So when we were over here and we created a distribution of means, it's because we had a sample and we had to compare apples to apples and oranges to oranges. So we did that math to create a distribution of means. Now the way we originally created the standard deviation for the distribution of means was this. We did a bunch of samples and then we calculated the standard deviation for this new distribution. But then a mathematician came along and said, oh, all you had to do was take the original standard deviation and divide by the square root of n. So what I'm telling you now is we need to create a whole nother one. We want to look at this distribution and how it's different from this one. So we have to create a distribution of mean differences. It's not that one, it's a whole new one. So the mean isn't the concern, and the mean is the mean is the mean. But we now need to come up with a standard deviation for the distribution of mean differences. That's our new goal. Which one's the problem child, the mean or the standard deviation? It's always the standard deviation. So this is where the whole day's purpose is focused today, is how in the heck do we calculate that? We could do a bunch of samples, blah, 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 subtract them, and create a new distribution of mean differences. But we can also do a mathematical approach, which I'm going to show you today. So the formula is going to be these two x bars minus these two mu's divided by the standard deviation for the distribution of mean differences. But now I have to show you how to get that. Because remember we translated that from sigma divided by the square root of n? It's going to be a much more complicated transformation here. So before I move forward, this is where I like to take a breath and say, where did I lose you? Because I know I lost some people there. It can get complicated. There's probably a better way to word that, right? What intelligent question do you have? Okay, yes, thank you.
Are we still going to be dividing by the square root of n?
We are. So, whatever we end up coming up with here, we're still going to have to divide by the square root of n because we're doing a sample.
Yeah.
So glad you asked. All right. So let's actually put some fake. Everybody so far we're good, right? Let me first, I'm going to make this an even better. The null hypothesis is? No difference. So we assume the null hypothesis to be true. So if the null hypothesis is true, which is no difference, what should this be in theory? If I assume the null hypothesis to be true, then theoretically this should be 0. They should be the same because there should be no difference. So if I'm assuming that New York College students are no different than Saddleback College students, then this should be 0. So we can take it off of our formula because that will be 0. So our new formula will be just the x bars divided by the standard deviation for the distribution of mean differences.
It's only if we fail to reject the null.
No, this is, right now what we're doing is theory, and the theory is what are your assumptions. Our assumptions are that the null hypothesis is true, and the null hypothesis is always that there's no difference, so this will always fall out. So we've now made it even smaller, which is great, and now I'm going to make it bigger. Yes?
So we don't need that, like, ever?
Nope, you don't need the mu. And again, just so in case, I like to allay fears, I'm not going to ask you to do any of these by hand anyway. But if you're kind of trying to understand conceptually why the formula works, this is why it works. Let's put in some fake data here. I'll put them in blue. Let's say that the standard deviation for the Saddleback College students is 10. Let's say that the standard deviation for the New York City College students is 15. Not too different. We don't go around assuming that the variability between people is different. Maybe Saddleback College students are smarter than the New York City College students, but there's no reason to believe that they'd be more variable, right? So variability between the two groups should be roughly the same. Now, we don't expect them to be exactly the same, but they should be roughly the same. So it's not a surprise if we have one is 10 and one is 15. It's not exactly the same, but roughly getting not within not too variable. But then let's say that I have 10,000 people in this group, and I have 100 people in this group. So my goal is to, when building the denominator of this equation, is to take both of my standard deviations, because both are legit estimates of the overall standard deviation. I want to take both of these and put them together to create an estimated standard deviation for the whole population. So which one should I pick if I were going to pick one, 10 or 15? If you felt like, I don't know, that's a weird question, I agree with you, we shouldn't just pick one. Why drop one and leave another out? We should probably use both, right? So that's kind of a trick question, sorry. But I'm going to use both. So how can I take 10 and 15 and create a single number that best represents both of them? Do we have a tactic for that?
You do a mean out of the two.
We do a mean or an average, right? So that would be 10 plus 15 divided by 2. Wait, sorry. Well, that's not nice. 10 plus 15 divided by 2. Does everybody see that? That's a legit approach, right? We take the 2 and we add them together, divide by 2. That'll give us an average of the 2 estimates of the overall standard deviation. But now looking at these, both of these numbers, I have a standard deviation of 10 out of 10,000 people, and then I have a standard deviation of 15 out of 100 people. Which one do you think is doing a better job at estimating the population?
The first one, 10,000.
The 10, because it's got a much higher number. Does everybody see that? Like 10,000 is a really big number. And so that's going to be doing a better job than, this one's not illegitimate, right? It's totally a good approach, but this one's doing better. So what we can do, instead of just saying 10 plus 15 divided by 2, let's weight them by their sample size. I'm just trying to, I'll do it on the outside. So this one I'm going to weight 10,000. This one I'll weight 100. And then I'm going to divide by, instead, 10,000 plus 100. So essentially I'm still averaging them, but what I've done is I've weighted them by their sample size. So I'm giving this one more value. So what that's going to look like is 10 plus 10 plus 10 plus 10 plus 10, 10,000 times. Plus 15 plus 15 plus 15 plus 15, 100 times. Divided by 10,100. So instead of it just being 10 plus 15 divided by 2, it's going to be all those 10s plus all the fewer 15s, 115s. And so now we're going to have an average, but you see how it's being pulled towards the 10 because there's going to be far more 10s than there are 15s. Does that feel solid? So it's like an average standard deviation, but we're weighting it by the sample size. The only thing is, we've discovered that the weighting is really good, but it's actually better if we use degrees of freedom. Does anybody remember how we calculate degrees of freedom?
N minus 1.
N minus 1. And so, Pearson is the one who said, you know what, this is good, but it's actually even more accurate if we do minus 1. This would be 100 minus 1. And then this would be minus 2 because we did the minus 1, minus 1. So essentially, instead of just saying a weighted average, well, so we're going to do the degrees of freedom times the 10, and then the 15 times the degrees of freedom, and then just divided by the total degrees of freedom.
Why are we using degrees of freedom?
It's slightly more accurate. So we're just taking one off of each of these tests, and by taking one off, it's just made it slightly more accurate. So because we're talking about 10,000 minus 1, it's really not impacting it that much, right? Because now it's 9,999 times 10, which is still a really big number. We just, by subtracting 1 from the sample size, we've made this whole calculation slightly more accurate. But I wanted to make sure that you understood why we weighted it to begin with before I did the minus 1. You kind of got that? You didn't get that. So let's say that I'll do smaller numbers. Thank you for saying that. I think it's going to be hard to say that, but there's other people who thought that. Let's just say I do, I'm going to have 6 participants in this group and 3 participants in this group. And then let's say they have all these different numbers. 5, 8, 6, 7, 5, 6. And then these guys have different numbers, 5, 6, 7. If I calculate their standard deviation, let's say that this number the standard deviation ended up being 2. I'll make this one, there we go. And then this standard deviation ended up being like a 1. Just to keep the numbers nice. With me so far? So if I wanted to pool them, or if I wanted to average them, I could have done 2 plus 1 divided by 2, which would be 3 divided by 2, which means on average I have a 1.5 standard deviation between these 2 groups. But this one had double the amount of people in it. And I'd like to give it more value because it's actually doing a better job at estimating the standard deviation because it has more people in it. So instead, I could have said, take this 2, and then I'm going to do it for each of the 6. So 2 plus 2 plus 2, 3, 4, 5, 6. And then this one, I'm going to have plus 1 plus 1 plus 1. What I've done is I've taken the standard deviation and weighted it by how many people were in the study. So by saying, another way of saying this would have been 2 times 6 plus 1 times 3. So I take the standard deviation and I represent it for each one of the participants that I had. So I have, the 2's represented and the 1's represented, and then I'm going to divide by 9 because there's 9 people total in my study. By doing that, I'm going to get a number that it's not going to be smack 1.5. It's probably going to be like 1.8. It's going to be closer to the 2 because I have all these 2's in there, pulling the mean towards the 2. But I'm still divided by 9, so it's not going to be completely 2. It's still going to be somewhat an average between 1 and 2, but it's going to be pulled towards the 2. Does that feel solid? So the reason why we weighted it by the sample size is to give this 2 more credit because it had double the amount of people in it. But then Pearson realized that it would be better if we didn't just stick with the actual sample size, but if we did the degrees of freedom. So in this case, it would have been 2 times 5, and then 1 times 2. So we just subtract 1 from each of the counts just to give it a slight more accurate numerator.
Because of the degrees of freedom.
Because it's degrees of freedom. So essentially what we're still doing is we're still weighting the average. It's a weighted average, but rather than strict weighting on sample size, we're weighting it on degrees of freedom. But the concept of weighting it by the sample size is pretty much the same. You feel okay with that? So this here, we don't call it a weighted standard deviation average because that's a lot of words. We call it our pooled, I'm running out of room, our standard deviation, and we call it pooled standard deviation. Because what we've done is we've pooled them, just kind of put them both in a pot and pooled them all together and then came up with a good number. I could have called it a weighted average, but that was a lot of words, so we called it pooled instead. You with me so far? So the pooled concept is we take our n, we're doing a's, a minus 1 times the standard deviation of a, plus nb minus 1 times the standard deviation of b, divided by n a plus n, well actually let me write it this way, na minus 1 plus nb minus 1. This is the formula that we just did here in blue.
So we don't have to do that.
You don't have to do it, but you're going to have to understand it. So let me get it on the board and then we'll start asking some questions. Now remember how I said, remember variance back in the day when we have squaring and square rooting? Notice I'm going to have some square rooting in my formulas. I'd like to keep this in its squared form until I know I'm totally done. So I'm going to do the pooled variance. So I'm going to square this one and then I'm going to use the variances here. So we're going to leave this in squared form until I'm completely done with my formula. So that I can square root at the very, very end. So again, my goal was to come up with an estimate of the standard deviation, and I'm pooling the two different estimators to create my own good estimate. So we're calling it a pooled variance. So let me ask you this about the pooled variance. If this one's 10 and this one's 15, what's the possible range of scores I could get for this estimator? For example, another way of wording that is, what's a number that would be too low? If I'm averaging the 10 and the 15, what's a number that would be too low?
9.
I agree with you 10, but the 9 is like legit off, right? Because it could not be 9. So we know the lowest it could get is 10, and that would just be because it's this, like if this one had also been 10, the lowest it could get is 10. And the highest it could get is 15. Now in this particular case, if we were to do the math, between 10 and 15, where is it going to be pulled towards? What is it going to be closer to?
10.
The 10. And why is it going to be closer to the 10?
Because there's more people.
Because there's going to be 10 plus 10 plus 10 plus 10 plus 10, 10,000 times, right. So it's going to be closer to the 10 because we have so many 10s represented. So this is called the pooled variance. So I could ask you questions about this in a couple different ways. Let's see why I wanted the whole board today. I'm going to erase this. You guys, no, I'll leave that. Let's do it here. So maybe I'll say something like this, and I'm going to use made-up numbers. But let's say I said, oh, the sample size is for A is 100, and the standard deviation for A is 15, and then the sample size for B is 10, and the standard deviation for B, actually let's do variance. The variance for A is 15, and the variance for B is 5. That'd be weird, but okay, let's say that's how that happened. If I were to ask you for the pooled variance, here are some possible answers. Now, first of all, you could do it mathematically. You could throw it into that calculation if you wanted. But you could also eyeball it. So we know this one's never right. But let's say my numbers were okay, which one of these could be your pooled variance? Or which ones should we cross off? We know we can cross off D. What about 16? How do we feel about 16?
Too high.
You think it's too high? What about 14? Maybe. What about A? Too low. See how we could. Now, what if I had done this instead of need more information? I could have done this. Oh, my brain is thinking. Now now you'd have to debate between 14 and 6. Which do you think? So we had just established that the range is between 5 and 15. So both 6 and 14 are within that range. But which one do you think is going to be the number that's the pooled variance?
14 because the population is 100.
14 because there's more people here. So it's being pulled towards the 15 because there's 100 people on this side and there's only 10 people on that side. So the pooled variance is going to be pulled up closer to 15. So again, you could have calculated it by hand, but you also can logically kind of debate that. So that's a great theory question on pooled variance. I might, you could calculate it or you could kind of logically process it. So this is our pooled variance, but we aren't done because all this has given us is this piece to the equation. We still, as your colleague pointed out, have to account for the fact that we've done a sample, so we still have to create the standard deviation for the distribution of mean. So we still have to divide by the square root of n. So what we end up doing is s of x minus x ends up being the pooled variance divided by the n for group A plus the pooled variance divided by the n for group B, and then we square root the whole thing. So by square rooting the whole thing, I've accounted for divided by the square root of n. This one, we normally talk about standard deviation units, but we left it squared so that we can square root at the very end.
And that's different from the stuff we were before.
These are all the same formula. So see the numerator, what we did, everybody gets what we did different here, right? We just dropped that piece out. Now this one is saying we have to do this divided by sx minus x. Well, sx minus x is this. This is this. So it's kind of an intense picture, right? So I'm going to erase this just to show you. I would never make you do this by hand, but this is what it would look like in its total package. Oops. You see why nobody likes this one?
Yeah, I know.
So this is why I focus on trying to make you understand why it works and how the pieces go together rather than just do it. This is where I differ from a lot of statisticians. They might say, now do it. So this is why we love JASP, because you're going to put the data in, JASP is going to do it for you. But what I might ask you on the test is, so maybe I'll circle in red what I might ask you on the test. I might do something like this, where I say, hey, how should my pooled variance come out? Right? That seems like a fair question. I might ask you this. Why do I have this piece in that formula over there?
Why?
Because I had to, no, I think it's great. Because we made a distribution of means. When we're doing samples, whenever we do a sample, samples, then we have to add the divided by the square root of n to the denominator. So that divided by the square root of n is now added to each of these just because we did samples.
That's what we sample.
Once we sample, we have to change it to divide by the square root of n. And then the rest of this is kind of an averaging of our standard deviations. And then what I'd like you to take away from this, though, is that what we've done in this craziness is no different from what we've been doing every time, which is this. I'll say it a couple times. What did I actually get? Minus what I hypothesized I would get. Divided by the standard deviation of that, and because it's a sample, divided by the square root of n. Every test I give you is going to follow that formula. What did I actually get? Minus what I hypothesized I'd get, divided by the standard deviation of this, and because it's a sample, divided by the square root of n.
That says that?
That's what this says. Now here's, I'll walk you through it, ready? What did I actually get, minus what I hypothesized I'd get, divided by the standard deviation of this, divided by the square root of n. What did I actually get, minus what I thought I'd get, divided by the standard deviation of this, divided by the square root of n. Every test follows the same format. And you think last time we only had one mean, and this was our formula. Now we have two means, look what the heck happened. Next week is going to be 3 or more means. So you can imagine what's going to happen. And so that's where it's on me to make sure that you understand what the formula is doing. Jess will do it for you. But your goal is to understand how is the formula working. So what did you get? Minus what we thought you'd get, divided by the standard deviation. Because it's samples, we have to add the square root of n. So they're all doing the same thing. It just gets more complicated the more complicated. Mic drop. It gets more complicated as the question gets more complicated.